Yes, I'm back. Yes, the kids had a great day and they wanted to know where the world's best ice cream, and I told them they're Kawartha Dairy. There you go. There's a free plug. I guess they're off to go get ice cream without me. Sad. What am I doing here? Hydrogen bonding. Just the whole idea there that water is a bent molecule, and you'll see there that oxygen is very electronegative, likes to scoop up electrons. So therefore, this is the big boss, and so the electrons will hang out at this side of the molecule. These poor hydrogens there, they lose control of those electrons for most of the time, not all the time. So this side of the molecule is kind of positive, and because of this characteristic, like there are these, and we're talking minuscule as far as time goes, like a billionth of a second, that there's this zzz, okay. But you have to think in a liquid phase there, all of these are moving, right beside each other, and if you have, there, it's such a weak force, this hydrogen bonding. But if you have 100 bazillion of them, now water, yes, it's a beautiful liquid, nice to swim in, but that's why if you again, sorry to use the same example, but do a backflip off a diving board, we've all done it, and it hurts because water has this quality to it. And so that's hydrogen bonding, holds our DNA together, very important stuff. And you'll see there, to form a hydrogen bond, you need a hydrogen. Okay, and you just look at this right here. You've got nitrogen, which is a very it's higher up on the electronegative scale, not as close to oxygen or fluorine, but it's in there. So therefore, as long as it's going to be able to pull those electrons away from that hydrogen for any amount of time, therefore now this becomes positive. So therefore now it can interact with hydrogen bonding. These ones here, this is a very negative end. It can interact, but not. It's not a hydrogen bond per se. It's just a polar molecule. Okay. You need a hydrogen to have hydrogen bonding. And here's a question. Okay, which of the following molecules would be expected to participate in hydrogen bonding? Here you've got an alcohol group. Perfect. There's that bent property. Okay, and that's what makes it. And just the presence of a single bonded oxygen to a carbon and then to another hydrogen there will create this bent aperture. All right. Hydrates. I added these here. They're just kind of cool to work with, and like all of the number crunching that we've done, and in some ways I do apologize because it's kind of a math course with a chemistry aftertaste, right? But it's important stuff. When you go on and do a bachelor degree and a master's degree, you'll be using the same principles. All right. These hydrates here, these are crystals. They look just like any other crystal, but they are weird ones here. They contain water molecules as part of the crystalline structure. Okay. What the formula lists the anhydrous without water formula of the compound first, and then the number of water molecules per structural unit afterwards. Blah, blah, blah. Have a look. Calcium chloride dihydrate. Okay. Now, that means that this is one unit. I'd say molecule, but it's not a molecule, right? So we call for ionic, instead of calling ionic crystals a molecule, we call them a formula unit, right? So this is one formula unit. So there's one calcium, two chlorines, and then there's two water molecules. And the interesting thing about these things is that you can cook them, and I mean just put some crystals into a plate, and put the plate onto a hot plate, and you'll have a reaction. What'll happen is the heat will make the water crystals evaporate, and you'll only be left with the calcium chloride. Okay, so to figure out the molar mass, you have to add everything up. So that's what I mean. I just want to make sure you guys got these here. In this here, there's 1 calcium, 2 chlorine. There would be 4 waters, okay, and 2 oxygen. So that would be the molecular weight. You add everything up, okay. You can get some good ones here. Calcium chloride dihydrate, like we just had. You can have iron 3 chloride. You know how to figure that one out, right? You reverse those oxidation numbers there. That 3 of the chlorine goes up there. Okay. This is iron 3 chloride hexahydrate. So just to be clear, if you had 1, okay, you wouldn't put a 1 in front of it. All right. It would just be calcium chloride monohydrate, dihydrate, trihydrate, tetra, penta, hexa, hepta, octa, nona, deca. If you need those, let me know. I'll throw them all down and for you, but there you go. So that's that one there. Have a look here. And just like what I was saying, you can cook this stuff up and the water will all evaporate. So you'll see here we have copper 2 sulfate, pentahydrate. Cook it, changes into copper 2 sulfate solid and 5 molecules of water. All right, and that would just be gone. So you'd weigh this, maybe you'd have 5 grams of this, and then you cook it, and afterwards there you have 3 grams. Okay, you'd have a lot more, you know, but some of the grammage would evaporate off. Okay. Here's a question here. Calculate the percent of water in Epsom salts. Epsom salts here, magnesium sulfate heptahydrate. So first you need to calculate the molar mass of the whole thing. All right. And then you need to calculate the molar mass of 7 waters and subtract that there from the total. Okay, so have some fun with that. Any issues, okay, let me know. Nothing outside your wheelhouse, just different bits of chemistry here that we're throwing at you. Again, what is percent water in this one right here shows you. Have a look. Acids and bases. We're coming back to this, and some of this, yeah, actually review will probably carry on to next week. It's the weird thing. I kind of have to introduce acids and bases and then leave it, and then come back, and then leave it, and then come back. And you'll see what I'm talking about there next week there when we get into equilibrium. Now you're getting into some real chemistry. And you guys remember there your 3 definitions there of Arrhenius, Bronsted-Lowry, and Lewis, acids and bases. I think there's a couple questions there on the quiz and the assignment. That's a great slide. You guys have seen this there before. The whole idea of an acid being a proton donor as opposed to a proton acceptor. Remember what this H plus is. It's just a proton, okay? A proton that just jumps from here onto here. It doesn't have any electrons with it, and it sits here like those are its 2 electrons, right? That's the whole thing. Ammonia is a weak base that forms the ammonium ion and the hydroxide ion in water. And, you know, in this case here, here's your ammonia, NH3. This water molecule donates a hydrogen onto here, so it becomes NH4 and now becomes OH. So you see how NH3 is a base, all right? It steals a proton from here, and the OH, the hydroxide, comes from this molecule, all right? So that's what we've got going on there. You'll see there that water can be an acid or a base, okay? Amphoteric, okay, can be an acid or a base, all right? In this case here, it's an acid because it's donating a proton over to the ammonia. So in this case here, ammonia would be the base, which it is. And then you'll see that on the other side, and I really like this, this is equilibrium. At equilibrium. We'll get to equilibrium there next week. you'll see there that in this case here, if the reaction is reversed, which one has the ability to donate a hydrogen? Well, this guy here can donate a hydrogen because it has one. But this one here has 4 hydrogens, so it's more likely to donate a hydrogen. So if the reaction is going this way, reverse, okay, this would be my conjugate acid. So just think, whatever molecule has the ability or does donate a proton, that is your acid. So this one here donates an acid, this one here donates an acid, and that would be your base and your conjugate. Okay. Lewis acid definition, there you go. There's an easy one. Reactions of acids, there's a whole bunch of them. I'm just going to go through a couple here. Acids react with metals there to give off hydrogen gas. Acids react with bases, as we all know, double displacement. Okay, neutralization reaction. Acids react with metal oxides like sodium oxide, potassium oxide, magnesium oxide, and they produce a salt and water. Okay. Ooh. Sodium hydroxide and potassium hydroxide, they react. Sorry, we missed one. There we go. Acids react with metal carbonates. And what's a carbonate? That's that one right there. CO3 2-. Oxidation number is 2-. So I got sodium carbonate. You can have magnesium carbonate, whatever, ionic. Okay. So here I got acid there with a carbonate, and you'll see what that one produces. Okay. C'est bon? Couple questions. Reactions of bases. Yeah, we just saw that one there. Bases there react with acids. Okay. And sodium hydroxide, potassium hydroxide react with metals. Okay, I'm not too worried about this one here, but just look at that one. Try and find the name of that one. Have some fun. Electrolytes, non-electrolytes. We've covered this. We're going to come back to it because today we can talk about strong electrolytes. Next week, when we're in equilibrium, we'll talk about weak electrolytes. You see, like going back to a strong acid, a strong base. Okay, what makes a strong acid a strong acid? Well, it's hydrogen. And that's why at the, where is my pH? I'm going to find that one. I'm just on a spiel here. So, there we go. You remember my dangerous acids are here at pH down at the lower end. My dangerous bases are down at the high end. Now, why are they dangerous at the extremes? Because at the extremes, they are all strong acids. Now, what does a strong acid or a strong base means? It means 100% breakage. Okay? So if I put hydrochloric acid, HCl, into water, that is going to break up 100% into hydrogen and chlorine. So I'm going to get maximum hydrogen. 100% breakage, strong acid, maximum hydrogen, dangerous. Strong base like sodium hydroxide, again, 100% breakage. Okay? And if you have that, it means you have maximum hydroxide, which makes it dangerous. We'll come back to that, but just getting into the whole idea of electrolytes here. Strong acids, strong bases, that's what we're dealing with there today. Okay? Because there is no equilibrium. Okay? I put hydrochloric acid into water, it breaks 100%. Bang. I put sodium hydroxide into water, it breaks 100%. Okay? Acids ionize, salts and bases dissociate. All right? But regardless, 100% breakage. There is no equilibrium when we're talking strong acids, strong bases. Weak acids, weak bases, there is an equilibrium. And it's like a fingerprint. Every compound will create a different equilibrium. All right, so that's why we'll talk about these there next week. Okay? Whew. That was a lot of hot air. You might want to pause it. So yeah, there's electrolyte, non-electrolyte. You guys can try these out. Which compound will not break up in water? Okay, acids will ionize. Okay, a salt will dissociate. A base will dissociate. And here I've got methanol, organic does not. Bang. Yeah, there's more on electrolytes here and how they break up. Here are some electrolytes examples. Okay, these ones here tend to be non-electrolytes, don't break up into their ions. Ionization is the formation of ions. Yeah, nothing too crazy there. You'll see there that here we've got phosphoric acid plus water, and you'll see there one of the hydrogens will jump on to a water. There's your hydronium, and now you're left with this. Okay, and now this can actually go again. H2PO4 minus plus water will produce H3O plus HPO4. Sorry if that didn't make sense, but you see I can take this one here and do another one and another one, because it's this is what we call triprotic, triprotons. This is a triprotic acid. You can have a diprotic acid. That's what makes this one here not a nice one, not a nice acid. Getting back into strong and weak. Okay, just the whole idea. Acids will break up, ionize 100%. Bases, strong bases, will dissociate 100%. And weak acids and bases, I say 50-50, but do not take that as reference. Okay, it's generally not. It's like 99 to 1, or it'll be 94 to 6. Okay, these weak acids are really, really weak. So, but we'll talk about these more next week. Okay, it's a good one. How did that jump so far? There we go. Again, these words, I really don't want you guys to get them confused. Please have I always throw a couple questions on the final there, about these, and just make sure that you keep them straight, okay? Because in chemistry, you'll hear them used incorrectly all the time, and it's okay, but just long as you guys know, okay? Dilute solution just means it's not a strong concentration. A concentrated solution means it has a relatively large amount. I don't really know what relatively means, right? Strong acid, 100%. A weak acid, partial ionization or dissociation. So a weak acid base there, partial. This is acetic acid, ammonia. These are weak. All right. Hydrochloric acid is a strong acid sold concentrated in 12 molar bottles, which can be diluted to a dilute 0.1 molar solution. You see all these words here? You just got to take them with a grain of salt. Okay. The acid strength, strong acids, I think we've covered this, 100% breakage. And you guys can see what happens here. Okay. Let's keep moving. Here we've got weak acids, again, 50-50, no. All right, it's a very, very small amount. So you look at this one, okay, actually, let's go back. Strong acids, and you'll see here that there is no equilibrium. I put hydrochloric acid into water, this thing, 100%, it's gone this way. All right, that's what we're doing there this week, strong acids, strong bases. You'll see here, though, I put vinegar into water. It's not 100%. Okay, some will ionize, and you'll see here that yes, this one here, this is the acetate ion. That hydrogen has jumped over there, but you'll also notice that there's a backward reaction as well. So some of them are not changing. Some of them are quite happy to stay like this and water. See, there's no ions, right? So, and at what percentage is it? This side 50%, this side 50%? Is it 50-50? Is it 70-30? Is it 80-20? Where is it? And that's what we're going to find out there next week. Okay, so that's your weak acids and your weak bases. Here's a link. I don't know. There we go. Table of acids and bases. Okay, and we're going to get into something called a Ka. value. We're going to introduce K there this week. KW formula. I'm sure you guys have seen it there before. And you'll see there that we're going to be dealing with some good numbers. So get your calculator out there for next week. It's a good one. Okay. These are all weak acids here. If you put them into water, they will not break up 100%. They will not ionize 100%. Okay, let's go. The strong acid, strong base, same thing, no equilibrium, 100% forward reaction. Weak base, there's your weak equilibrium, okay, forward and back. And we'll be using something there next week called KB. Okay, so K is the, let's call it the universal symbol for equilibrium. All right. Salts dissociate. Okay. We've got hydrochloric acid, sodium hydroxide produces salt and water. Okay, it's the end product there of an acid-base reaction. Ionic salts here, metal plus, non-metal minus. Here are some questions there you guys can have a look at. Pause it. Please have a look. I'm just trying to get through, so I don't need to take much of your time. But you guys can pause this, have a look. They're good questions there to help. Same questions you'll see on the final. Okay. Dissociation there of electrolyte. We've talked about this, how aggressive water is. Okay, and how it just takes apart and the water actually holds. See, if I put salt into water, I get sodium plus, chlorine minus ions. And you'll see there that chlorine is negative, so it'll be supported by the hydrogen sides of the water because they're positive. You see how it works. More on salts there. Okay, salts dissociate into at least 2 ions. So you see here, if I have 1 mole of sodium chloride and I put it into water, I have 1 mole of sodium ions and 1 mole of chlorine ions. So if I put 1 mole of sodium chloride into water, I get 2 moles of ions. Get it? 2 moles of ions. Look at this one. Calcium chloride. I put 1 mole into water. I get 3 moles of ions. 1 and 2. Hopefully you see that. More practice. Have a look. Soaps. Soaps are salts. They have a non-polar organic chain of carbon atoms at one end and either a sodium or potassium salt of a carboxylic acid group at the other. Okay? To make an effective soap, the acid must contain 12 to 18 carbon atoms. If it contains fewer than 12, it will not be able to mix well and clean oily dirt. And you'll see what's going on here. Oil and water don't mix. Well, this is the solution to that. And you'll see here, there's your polar, okay, which likes the water. Here's your non-polar, which likes the fat, the grease on your hands. You get this going there with a little water. It doesn't work if you don't agitate it. You've got to work this in, and what this will do, it'll just break up all the little bits and pieces and make them small enough so that they're able to be washed away. Okay. There's pH and pOH. Okay, this is your pH scale, which we introduced there last week. And, the smaller the pH, the increase in the hydrogen ion concentration. The increase in the pH scale is an increase in the hydroxide ion concentration. Just to let you know that there is also, along with the probability of hydrogen scale, there's also the probability of hydroxide scale. Okay, and it's just the exact same thing, just in reverse. Okay, and yeah, so you'll see your pH scale, which is going the same way, as pH 0, pH 7, pH 14. So on the top half here of this, same scale, 0, 7, 14. But on the bottom half is your pOH. It's just the exact reverse. So what was pH 14 base is now pH 0. So dangerous, just flipping it around. Okay, and just to let you know that, actually I'll show you. There you go. pH plus the corresponding pOH always equal 14. And this, you ever wonder where the pH scale comes from, 14? Okay, it comes from this formula here. Sorry, the equilibrium there of water. And what happens here is at any given temperature of water here, doesn't matter what we're talking about, any type of pH of water, if I multiply the hydrogen concentration times the hydroxide concentration for any solution, any water at any pH, I'll always get this number. So if you if you measure the hydrogen concentration there for a pH 3, okay, 10 to the minus 3, all right, times 10 to the minus 11. Okay, where did I get that from? 3 plus 11 equals 14. Okay, what we're talking about here, the concentration of any solution, if you measure its hydrogen concentration, and of that same solution, measure its hydroxide concentration, you get one of the constants of the universe, and that is this number, 1 times 10 to the negative 14. And it's based on this number here that through logarithmic scale, we're able to utilize that into a pH system. Okay, so that's the basis there. That's a good little formula. You'll be needing that one. pH plus pOH is always equal to 14. It's just a derivative of the two scales utilizing this formula. Yeah, here's another formula that you guys will be using. pH is equal to the negative log of the hydrogen concentration. Okay, so whatever your hydrogen concentration is, pop it in here, do the negative log of that number, and there's your pH. This formula may look different, but it is exactly the same as this formula. These two formulas are exactly the same. It's just this one here is written in terms of pH, and this one here is written in terms of hydrogen concentration. So here I'm going to give you the hydrogen concentration, and I'm going to ask you to give me the pH. Plug and play. In this particular case here, I'm looking for the hydrogen concentration, so I'm going to give you the pH. I'm going to give you the pH. You're going to plug it into your calculator. It's weird, okay? 10 to the negative exponent. Figure out how your calculator does that. That's a weird one, okay? Hopefully these formulas aren't too bad. I'm sure you've seen them there before, but if they give you any trouble there, just let me know. Measuring the pH of a solution, litmus paper, okay, turns red with an acid, blue in paper. There's also universal indicator, okay, a multitude of nice colors there that color coordinate to a nice chart. pH meter is a great one. The one I find works great is boiling cabbage juice. Boiling red cabbage. You get that red cabbage juice. Honestly, works like a charm. It's just amazing, and it works every time. Blood pH, in order to carry out its many functions properly, the pH of the blood must be remain. I would even, that's even cutting it a bit close there. Anything out there outside of this, you're looking at acidosis and alkylosis. Acidosis, if your pH is lower, usually your pH is about 7.4, 7.48, somewhere in there, and not very far outside of that range can you be in big trouble, okay, on either side, okay, acidosis or alkylosis. The main reason for this is that enzymes, they're the protein molecules that act as catalysts for many reactions in the body. They don't really work outside of that pH range. So, and if you don't have proteins working, you're done for. Your blood contains compounds called buffers there that enable small amounts of acid or bases there to be absorbed. And the main buffer is the body's just amazing, absolutely ingenious. Carbon dioxide, which is being released by all of your cells of your body, it's a waste product. It's going to the lungs to be expelled. It's garbage. But the body, okay, uses an enzyme there, converts CO2, okay, from the journey from my big toe to the lungs only, converts it to bicarbonate, which then acts like a buffer to maintain blood pH. And then when it makes it up to the lungs, it gets changed back into CO2 and expelled. Amazing. Amazing. Yeah, you guys can have a look at that. Blood plasma. Beautiful. Love it. Here are the pH formulas there. I've already introduced them. Okay, these two are the same. Okay, pH plus pOH is equal to 14. There's your KW formula. Okay, the hydrogen concentration times the hydroxide concentration of the same solution will always give you this number. And as with pH, sorry, where am I looking at? Yes, as with pH, there's a pOH. I don't think I'd put this on a final exam, but you never know. And this just shows you how to do this. I think there's even helps you there with a little bit of calculator stuff. Okay, let me know if you guys have any issues with that. pH there for known hydrogen concentrations. So calculate the pH of a 0.015 molar hydrogen concentration. So, okay, I know the hydrogen concentration, so I plug it in. So here I gave you the molarity of the hydronium ion, and that I just plugged right in there because that's the formula. pH is equal to the negative log of the hydrogen concentration, and I got a number there of 1.8. Good. Next question. Now, what is the pH of a 0.020 molar hydrochloric acid solution? Okay, well, it's my formula for pH. pH is equal to the negative log of hydrogen. Well, I don't know the hydrogen ion concentration. But you do, because hydrochloric acid is a strong acid. Okay, so any of those strong acids there that were listed there above, that's the trick to this one here, is that if I give you a question like this, what is the pH, this molarity of hydrochloric acid? Well, hydrochloric acid, there is no equilibrium. All of the hydrogen is available. So if I had 0.02 molar hydrochloric acid, okay, HCl breaks into HNCl. Okay, so here, remember this slide right here, I'll show you. Oh, if I can find it. Yes, you remember this one right here, sodium chloride broke into sodium and chlorine. Well, what if I just change this right here and put hydrochloric acid changed into this? So this is exactly what's going on in my slide there, which I got to find again now. So if I have 1 mole of hydrochloric acid, that means I have 1 mole of hydronium, right? You agreed with me before. You have to agree with me now. All right, so in strong acids, let's go back to this now. Yes. So what is the pH of 0.020 molar, a lot of zeros there, molar hydrochloric acid solution? This is hydrochloric acid. It's a strong acid, so whatever the molarity of that is, that's going to be the molarity of your hydrogen concentration. Okay, strong acids only. That's what we're dealing with there this week. Next week, weak acids and bases. So in this case here, plug and play, put your 0.020, a lot of zeros in there, and get your number 1.7. What is the pH of a solution of sodium hydroxide that has a hydronium ion of 2.5 times 10 to the negative 11? So there's your hydronium concentration. Bang. There you go. Here's that formula there, the ion product constant. And as we said, if you measure the hydrogen concentration of a solution as well as its hydroxide concentration, multiply them together, you get this constant of the universe. Okay? In an acidic solution, the hydrogen concentration is greater. In a basic solution, it's reversed. I think we've covered that. Just to let you guys know there that this pH plus POH, I just wanted to show you there that they do add up. And the if you play with it, it's just there might be a question. Yeah, there'll be a question out there on it. But the pH scale plus its corresponding POH scale will add up to 14. Just a silly little question, but there'll be one on there. So here we've got calculate the hydrogen in a 0.0152 molar sodium hydroxide solution. Now wait a second. Look at this question. Calculate the hydrogen concentration in a basic solution. Okay, so this is a strong base. I'm going to have 100% dissociation, so that means that this is a 0.0152 molar solution of sodium hydroxide. It's a 0.0152 molar solution of hydroxide. Remember that? We just did it there with the acid, right? So I'm measuring, I have a measure to find out how much hydroxide, but the question is asking me for this. So that's where we use this KW formula, okay? And this number here, we already said that it is exactly the amount of hydroxide, so you just plug that in here, okay? And you had two unknowns, now you only have one unknown, now you just flip it all around and away you go. So this is my hydroxide formula. This is what we're looking for here. Tells me it right there because I'm solving for that now. That tells me my my hydrogen concentration, and there we go. Let me know if that wasn't clear or if that was clear as mud. Shoot me an email. We'll talk about it there next week anyway. But you'll want to know, you want some clarification, shoot me an email. Or just pause it and rewind it and watch it again. Calculate the pH of kind of the same thing here. And this is just a play on here. Remember, I gave, and basically this is what I'm doing. I gave you the hydroxide concentration. Okay, but I'm asking for this one. So you plug it into this formula, solve for the hydrogen concentration. The next logical next step to this question is calculate the pH. Well, now that you have utilized there and found the hydrogen concentration, plug it in and away you go. There are other ways to do this. You can utilize the POH formula. Okay, I gave you there the OH concentration, but you can actually utilize the POH formula. POH is equal to negative log. Delete that or just fast forward if that's confusing you. It's all good. Another question, same thing there. Perfect. Okay, you guys can have a look at that one. Let me know if you guys have any issues. There's another one there. We're just moving and shaking. All right. Titration. The whole idea there of well, what we're talking about here is measuring the volume of basically an acid against a base, or one thing that's reacting with another. And usually one of them will be an unknown. Okay. And like a titration is used there to determine the amount of acid or base present in a sample. You see, one of them will have a known concentration. The other one there will have an unknown concentration. Basically, the only thing, we'll have is basically the chemical formula, the chemical equation. But I'm missing how much I need, and it's all based on concentration, right? So what we do is we slowly titrate. We slowly pour one into the other using an acid-base indicator. And yeah, it's a nice one. there's the movie there. I'm not going to play it. You guys can all watch that. It's a great little movie. Okay, it shows you everything. Moving on, the titration formula is the same formula there that we had used there before. Okay, you guys have seen this there for dilution. And we're using the same formula again there for a different purpose. So you have a look here. If 22.59 milliliters of 0.1096 molar hydrochloric acid is used to titrate 25 milliliters of sodium hydroxide, okay, to a phenylalanine endpoint here. Okay, that's your acid-base indicator. What is the molarity of NaOH? Okay, so you're thinking, oh my goodness, what's going on here? First, you have a look at your chemical equation. Hydrochloric acid plus sodium hydroxide, okay, produces water and salt. Got it. Now, what information? What's going on here? Knowns, I've got 22.59 milliliters of this molarity of hydrochloric acid. Okay, so I have both bits of information there. I got 25 milliliters of sodium hydroxide, and they're asking me for the concentration. What is a molarity? All right, so it's just a matter of plugging and playing. Okay, no different, just a different use of the same formula. Okay, and any issues with that, let me know. Just remember, change those there to liters. Make sure that everything's in liters. Okay. Now, this one here was for 1-to-1. And you'll see here there that your chemical equation with the formula, okay, 1 mole, 1 mole, there you go, no worries. What if you have something like this? Okay, what is the molarity of sodium hydroxide solution if 21.93 milliliters of sodium hydroxide is required to titrate 26 milliliters of 0.5 molar oxalic acid? Okay, so here I have oxalic acid. Here I have sodium hydroxide. Okay, all right, fine. But wait a second, molar ratio 1-to-2. Aha. All right. So basically, you're going to do the exact same thing as number 1. You're going to follow the same procedure. Okay, there's 4 unknowns here. I'm going to give you 3 of them. You plug and play. And that's what's going to go on here. But at the end, look at the molar ratio. It's not 1-to-1. So in this case here, we would need to double the answer. And you see again, there's my 4 unknowns. I gave you 3 of them. Okay, you're solving for the 1. All right, you get your answer. But before you choose A, B, C, D, make sure that if it's a 2-to-1 ratio, you may need to adjust. Okay, so this was for the molarity there of the sodium hydroxide. Okay, so we found that the molarity in question was 0.5928. But since there's 2 of them, we need to double that. That's it. Just that's the trick. Now you know it. Oh, cat's out of the bag. All right. There's more of these here, and you can see it's the same question. It's the same question using all these different other bits and bobs of information. If 22.59 milliliters of 0.1096 molar hydrochloric acid, blah, blah, blah. If 22.59 milliliters with 2.47 times 10 to the negative 3 moles of hydrochloric acid. You see where I'm on? So everything carries through. And you guys are experts at this anyway, so. More practice. Have some fun. Neutralization reactions. We're almost done here. Geez, that wasn't too bad. Neutralization, acid-base, produces salt and water. Now, total ionic equation. So here we're dealing with ions. This may be a new concept. So, remember last week there, remember I introduced to you aqueous, liquid, solid, now they come into play. There is a bit of method to my madness. Might be more madness than method, but the That's where we're coming into play now. So have a look. Here I got hydrochloric acid, aqueous. Okay, that's a solution, right? I put some amount of hydrochloric acid into a lot of water. Sodium hydroxide aqueous solution. Here I got water. It's an L because water is not a solution. It's a liquid. It's a compound. And sodium chloride aqueous. All right, so here I have 3 solutions and this one here. So let's break them. Anything with a solution gets broken. Okay? Break it. Break it. And that was on the left side of the arrow. Please make sure that everything stays on the left side of the arrow. Now the arrow, now we're moving on to the right side. Anything that's liquid stays liquid. Anything that's aqueous gets broken. Perfect. Now I call it the slice and dice. All right. Now, and I want to, let's have a look here. Wait. Okay. Sorry. Just need to do a little bit here. All right. Slice and dice. What do I have the same on both sides? Do I have a H plus over here? I got no H plus there. No. Okay. Do I have a chlorine here and a chlorine? Yes, I do. So, chlorine, gonzo. Sodium. Do I have a sodium here? Oh, I have a sodium there. I have a sodium there. Is there anything else to slice and dice? No, that's it. So my net ionic equation is whatever is left over. Okay? And it should add up. Not too bad, eh? You can read about that there, writing net ionic equations. There's really not much to it. If you just follow the patterns there, formula equation, there's your total ionic equation. Do some slicing and dicing where you go. And see, in this case here, we have solid. Solids don't get broken up either. Okay? Yeah, and there's more here. Practice there on your own and have some fun with it. And there's some more practice. Thank you guys, and really I appreciate your patience in this week. Wasn't a great week, but we managed to get through. And if you guys, I'll, as far as I can give an extension of a day or so. And I'll make everything due there the Friday for next week. So hope you guys are well. Take care. Let me know if you guys have any issues, and see you next week. Ciao.